Hey everyone, and welcome to The Explainer. I want you to think about your day for just a second. You woke up, probably checked your smartphone right away, worked on a laptop monitor for hours, and there's a good chance you'll end the evening relaxing in front of a TV. We are officially addicted to glowing rectangles. We rely on them for literally all of our human-computer interaction, and yet we rarely stop to appreciate the absolute physics magic happening just millimeters beneath that glass. So let's dive right in and unpack the fascinating science of modern display systems.
Here is our visual roadmap for today. We're going to start with the magic inside screens, look at emissive versus non-emissive tech, dive into OLEDs, step up to AMOLEDs, explore QLEDs, and then finish up with the ultimate display showdown.
All right, part 1. The magic inside screens, the building blocks of display technology.
Okay, so the fundamental goal of literally any display is to take electricity and convert it into light that our eyes can easily perceive. To pull this off, modern screens rely on two foundational types of materials. On the left side, we have photoactive materials. These interact directly with light. They absorb it, emit it, or convert it through amazing processes like fluorescence. They are absolutely crucial for generating light and enhancing color. Then, over on the right, we have electroactive materials. These respond directly to an electrical field. They handle the heavy lifting of charge transport and electroluminescence. Simply put, your photoactive materials deal with the light, while your electroactive materials respond to the electricity.
Moving on to Section 2, Emissive versus Non-Emissive, the Great Display Divide.
Let's compare the two major categories here. Think of non-emissive displays, the ones on the right, kind of like a stained glass window. Now, a stained glass window doesn't glow on its own, right? It needs the sun or some external backlight shining brightly through it to work. Non-emissive displays just filter or modulate that external light to create the image you see. They give us incredibly high brightness, but the screens are generally a bit thicker because of that extra light layer. Now, emissive displays on the left, totally different story. Think of them like millions of tiny, independent glow-in-the-dark stickers, but controlled by electricity. Every single pixel generates its very own light. Because they skip the bulky backlight entirely, they can be ultra-thin. Plus, they offer unbelievable contrast, because to show the color black, the pixel literally just turns itself completely off.
Which brings us to Section 3, OLED self-emissive pixels, the power of organics.
So, OLED. It stands for Organic Light Emitting Diode. Take a look at this incredibly precise, microscopic sandwich structure. What we have here are several organic semiconductor layers packed tightly between two electrodes, the anode at the very bottom and the cathode at the top. You've got specific layers dedicated entirely to transporting holes and others just for transporting electrons, and they're all funneling down to that yellow emissive layer right smack in the middle. Remember, there's absolutely no backlight here. The light is born right in the center of this stack.
Let's break down the actual physics of how this electroactive marvel comes to life. Step 1. Charge injection. We apply a voltage, injecting electrons from the cathode and creating positive holes from the anode. Step 2. Charge transport. Those electrons and holes start traveling toward each other through their respective layers. Step 3. Recombination. They finally meet in the emissive layer and combine to form this excited state called an exciton. And then, the magic moment. Step 4. Light emission. That exciton is highly unstable, so it quickly drops back down to its ground state. As it does that, it releases its excess energy as a visible photon of light. This whole incredible sequence, that's what we call electroluminescence.
So, we have this amazing organic material that glows brilliantly when we shock it with electricity. But here's a massive challenge for you to consider. A modern smartphone screen has millions of these tiny RGB subpixels. How on earth do we supply and perfectly regulate the exact right amount of current to every single one of them millions of times a second without the screen just flickering out or failing completely?
Let's answer that in Section 4. AMOLED, Active Matrix Precision, the smartphone standard.
The secret to controlling all those millions of pixels is the AM in AMOLED, which stands for active matrix. And the real hero of the active matrix is the thin film transistor, or TFT. Working alongside a little storage capacitor, the TFT acts as an individual, highly precise electrical switch for every single subpixel on your screen. Instead of just scanning rows and columns sequentially like the clunky passive screens of the past, this TFT backplane allows each individual pixel to be actively maintained at a very specific brightness level between screen refreshes. It's a total game changer.
See how the active matrix actually integrates with those organic layers we talked about? At the very bottom of the structure, sitting on the substrate, beneath the anode, is the TFT array backplane. It acts like an intelligent gatekeeper, It supplies the exact perfect amount of current up into the organic stack to drive those electrons and holes together to make light. Now, because that TFT array takes up valuable real estate at the bottom, a lot of modern AMOLEDs use what's called a top emission structure. That basically means the light shoots upwards, right out of the cathode towards your eyes, which allows us to pack the pixels together with an incredibly high density.
Because every pixel is self-emissive and actively controlled, AMOLEDs give us those famously deep blacks, super fast response times, and sky-high refresh rates. Plus, since there's no rigid glass backlight needed, the entire structure can literally be built on flexible plastics. That is exactly how we get today's amazing foldable phones. But, there's always a catch. Because the emissive layer is made of organic compounds, they can degrade over time. The blue OLEDs in particular age faster, which can sometimes lead to that annoying image burn-in.
So organics are phenomenal for ultra-high contrast flexible screens. But what if we completely flip the script? What if we wanted unparalleled, blinding brightness and a screen that practically never degraded? What if we just stepped away from organic materials entirely? That leads us right into Section 5. QLED, Quantum Dot Brilliance, Manipulating Light with Nanocrystals.
Okay, QLED stands for Quantum Dot Light Emitting Diode. To really get this, you absolutely have to understand what a quantum dot actually is. We are talking about incredibly tiny, nanometer-sized semiconductor crystals. They are the ultimate photoactive materials. When you shine light on them, they get excited and re-emit their own light. But here is the mind-bending part. A quantum dot's color has nothing to do with dyes or pigments. Its color is strictly determined by its microscopic physical size. Small dots emit blue, medium dots emit green, large dots emit red. We are literally tuning color by changing the physical geometry of a crystal. How cool is that?
Now check out the very bottom layer of this QLED stack. We have a blue LED backlight. Yep, you heard that right. This means QLED is actually a non-emissive display technology. The pixels themselves aren't generating the original light. Instead, that blue LED fires light upward, which then smashes into that incredibly important quantum dot layer filled with red and green nanocrystals.
Let's trace the full journey of this light. We're going to use a process called photoluminescence to magically transform a basic bright blue backlight into a stunning, full-color television image. Breaking that down into 4 simple stages. First, the backlight fires off its blue photons. Second, those blue photons strike the quantum dot layer, transferring all their energy. Third, the different-sized quantum dots wake up and act like highly pure color factories, re-emitting perfect red and green light. Meanwhile, some of that original blue light just passes straight through the gaps. So now we have an incredibly pure mix of red, green, and blue light. Finally, stage 4, a traditional LCD layer acts like a microscopic shutter system, controlling exactly how much of that pure RGB mix passes through to your eye to form the final image.
Let's wrap it all up in Section 6, the ultimate showdown, OLED versus QLED.
So, the million-dollar question, which is actually better? Well, it really comes down to how and where you use it. OLEDs, using self-emissive organic materials, give you absolutely perfect, true blacks because individual pixels can literally turn off. But they top out at moderate brightness and carry a slight risk of burn-in after years of heavy use. QLEDs, on the other hand, rely on those inorganic nanocrystals and a powerful LED backlight. They can get incredibly bright, making them perfect for a sunny living room. They also don't really suffer from burn-in, meaning a longer lifespan. But because there's always a backlight shining back there, their blacks just aren't quite as perfectly pitch dark as an OLED.
The biggest takeaway from this explainer is this. Whether a screen relies on the precise charge transport of electroactive organic layers or the photoluminescence of photoactive semiconductor crystals, everything we do in the digital realm comes down to perfecting the pixel. Mastering these photoactive and electroactive materials is the silent, ongoing engine driving modern technology forward.
And that leaves us looking right at the edge of tomorrow. We've gone from bulky, heavy glass tubes to flexible plastic layers and microscopic nanocrystals. As we keep pushing the extreme limits of these materials, making our display systems thinner, brighter, and way more efficient, it really begs the question, where exactly does the screen end and the real world begin? Will the displays of tomorrow be woven directly into our clothing, or perhaps projected cleanly onto our own retinas? It is a wild, fascinating future to imagine. Thank you so much for joining me on this explainer today. Keep asking those big questions, and I'll catch you next time.